believe that these OPs dispel the myth of irreproducibility, because when you plot it this way, you see which ones work, which ones don't work, and otherwise people say it's chaotic. Finally, if you drive beyond the peak, it doesn't improve the production because you're turning on other loss mechanisms. We can skip over this. Let me just talk about co-deposition. This quasi one-dimensional model, those equations I showed you, have been incredibly helpful for us. We were able to design co-deposition in 1989 and other techniques which I'll show you. Our co-deposition is a little different from what's done at Spey Wars, which you read about. We use palladium, and they tend to do co-deposition on other materials. And what happens is as Peter points out, the important thing about co-deposition is you get, here we're looking at the logarithmic loading ratio here as a function of time. We get rapid loading with co-deposition either way, either with the Spey Wars variant or what we do. Both of them give you a rapid rise time on the surface of loading. The difference is because we end up using palladium as the substrate, we then get diffusion deep. And so ours falls down a little bit. And these are the equations. These are just like before. There's a diffusion flow equation. We can talk about a palladium flow equation. Yes, Peter?
And Joe, how do you determine your loading in a co-deposition experiment?
Well, it's so heterogeneous, you can't. I mean, you can make a calculation based on resistive ratio, but I don't believe that a single value holds for the entire volume at all.
So these are resistance ratio measurements plotted here?
No, this is theoretical calculation. This is not measured. This is the, look,
okay.
Here's the flow equation for deuterons. Here's the flow equation for palladium. This is the diffusivity of palladium, the concentration gradient.
The issue was this, nobody's got a good way to measure the loading in the co-deposition
Correct.
experiments. Okay,
No,
I'm asking about that.
this is a brute force calculation is where this comes from, which is why I put the equations up here. Sorry for not making that clearer. The important point here is that there are three types of cold fusion. I mean, two co-deposition variants and classical cold fusion without. This is a calculated thickness of the co-deposition layer, and the measured energy gain. We can see that as we add the calculated thickness, that we're getting more energy out. One other thing we get here, we can see the fusor. When it turns on, we're getting we get illumination in the near infrared. We'll come to that in a second. Take-home point. There's more than one kind of cold fusion in the sense that there are different types of loading. There's co-dep as well as classic. I think we'll skip this stuff. We're not going to have time. Yeah, we're not going to have time. I'm going to skip this. Questions? Yeah.
All the numbers for the optimal operating point from the slides that I could understand seem to be around 5 watts, and that seemed to be independent of the experimenter. Does it not depend on the physical dimensions of the device?
Yes.
Yes,
Yes.
it does, or yes, it doesn't?
Yes, it does depend. Yes, it depends on many things, and I think it's just happenstance that they overlap there. Peter?
In terms of the deuterium flux argument, your focus is on in terms of your electrophoretic mobility arguments, you're focusing on what's going on in the electrolyte. And we tend to be more interested in the flux inside the cathode. Now, I'm of the opinion that the thing that's special about your user is that you have a place where the current comes in, and then very close nearby, you're making gas, so the currents, the deuterium currents turning around, if you like, coming back out. And I wanted to emphasize that that's fundamentally different than what happens in Fleischmann-Pons experiment, the SRI experiments, or any Frascati or energetics, pretty much everybody else's experiment. What Fleischmann-Pons tried to do is to have the anode sort of be reflected uniformly around the cathode in order to make as uniform as possible the deuterium entrance into the cathode to maximize the loading. But by doing it, if you like, it minimizes flux, because the only flux you get is the local flux due to the deuterium coming in. In your experiment, if you like, because of your arrangement, you've got a single point anode, and you get the field lines which gather together in the closest point of the cathode. You have a focusing of your deuterium to a local point in the cathode. So if you like, you maximize your local current as you jack up your local current density a lot. And then you've got all kinds of places for the deuterium just to go. So you've got a local, not only have current density, you've got a flow, a directional flow near the surface. And if you like, I'm reasonably convinced that's why your user works as well as it does. That is the part that, in terms of flux, that's magic. The other part you got your user stress and strain, which helps lower the energy for vacancy information. So that's the other piece of the magic.
I think you're right. I couldn't have said it better, except I'm going to try to now. Here, for example, this section is on metamaterial, so we're exactly going to talk about what Peter brought up. This is the classic, we're looking down on the anode-cathode system. This is supposed to be electric fields, where here we see the electric field go from the anode to the cathode, like that. And as we'll see, we'll go through this in a bit, which is just what Peter says. Here's our arrangement with the fusor, and we're going to get an electric field intensity distribution that's very different between the classical FPE cells and what we do. And so let me go to that now. Beginning in '89, we tried many designs for the electrodes, and we got excess energy from some, but one really stuck out. Here what we're looking at, this is break even. I mean, here's platinum, platinum. We never got any excess energy. Iron, iron, aluminum on platinum, yada, yada. This here we get excess. But the fusor is just great. So the question is why? And this, I think I would only add one thing to what Peter says, which is the other thing that's different is by having a high resistance solution, we change where the things go as well. And I'm not sure that we would see the same results if we salted in the solution. So we first presented this back in at ICCF 10, and I'll show you the pictures in a second. What is a metamaterial? When I went to college here, we didn't have these, and they were recently discovered mainly for optical devices. And what was discovered was shape matters. You can take a material which has its properties, material science, and if you change the shape, you can change the expectations of what's seen. So for example, in optics, you can make negative refractive index materials, negative group velocity, anomalous reflections, cloaking, all kinds of things that you couldn't make if you didn't change the shape. So we wondered, are we doing that with the fusor? And in fact, we looked at our fusor, we did an analysis based on the fact that the solutions were ranging between 220 and 500 kiloohms. The resistance in the cathode was this. We did a little analysis using Laplace. You can read all of this. We don't have a lot of time. And what we discovered was there are major electric field differences in the distribution between the wire-wire systems. I mean, Peter was describing we're in the Fleischmann-Pons system where you have the cathode in the center, you have the anode going around it symmetrically. But it turns out you also get symmetries that shut it off just with two wires. So for example, here's our classical two-dimensional, we're looking down on the wires. So the cross-section of the wire is going to just be this circle. Here's the anode, here's the cathode. Very different from the fusor. I'll show you blow up as best I could. The important thing is, just as Peter correctly noted, we are creating flux within the metal rather than equilibrium. In the classical two-wire system, or the Fleischmann-Pons system, where the anode circles around a single wire, it is very different from what we see with the fusor. And if the program I did, this is supposed to be a little arrow. It's a circle instead of an arrow, but it's the same thing. And what you see is, in a classical system, you are not going to get a net flux through the metal. It's going to all reach equilibrium around it. You're going to get a certain loading, but you won't get a net flux through it. And that is very different from what we see here, where we have it enter one side and it comes out. And we might get a little loss here. That's where the, yes?
So, Mitchell, if this is coming from a solution Laplace equation, this sort of qualitatively doesn't really correspond to your experiment, because your experiment, the bubble formation is localized at a point.
Is what?
In your experiments, the bubbles are coming out at sort of a single point in your cathode, not over a band.
Over a line. It comes out over here.
Yeah, but it's more localized than this calculation really does.
Yes. The-
I'm wondering whether maybe you've got, maybe the Laplace equation by itself isn't what's going on here. Maybe you've got charge that's mobile in the electrolyte. You got some screening, you got some additional effects beyond Laplace that's helping to localize the current on the surface of your cathode.
I think you got your work cut out for you. We're going to have to analyze that too. This is what we see as a line when we get the excess energy. Now, we were looking down before. These are where the bubbles are. We're looking down on the fusor here. And I didn't do the correction that you said, but we obviously should do it. In this simple analysis, what we see is a change of the distribution. And I'll show you a picture in a second. When we get the bubbling elsewhere, when we get the gouda bubbles, as I can show you here, the excess energy turns off. We see three stages. So pre-cold fusion we see here. Here we see the earliest bubbles. And if we end up either salting or overdriving, we see the bubbles everywhere. The take-home message is, by whatever method it works, it does work. We do see that when we use a high impedance solution and a curved spiral cathode, which may also induce cold working, like you point out, I suspect, we do see these effects. In fact, let me do the movie, if you haven't seen that yet. Let's just go back here. I think we showed this at the beginning. Here's a close-up. For a couple of years, we were putting in situ cameras everywhere. But it turns out, after a while, you collect gigabytes and gigabytes of data, or of imaging data, and I'm not sure what good it is anymore, so we actually stopped imaging, except when we measure near infrared. But here you can see it does occur only on one side, and if we were getting a gout of bubbles over here, the excess energy would fall. We don't have to go through the whole. Any other questions?
You mentioned that you use a solution of deteriorated water. What salt is in the solution, if you can tell?
We add no additional salt. In fact, when I do the fusors, we pay extra to get what's called low paramagnetic heavy water, where the heavy metal ions are taken out. I spend as much time as I can to try and make this as pure as we can in the solution.
Okay, so there's no solution. It's just as pure as you get.
There's no additional ions added, but it is a solution.
In
Yes.
Fleischmann-Pons initial experiments, they had 10th molar lithium deuteroxide And in subsequent applications, people go to like 1 molar lithium hydroxide. And Mitchell's sort of off by itself, sort of the only one working with salt here for these experiments.
Well, we look forward to their demos too.
As you mentioned before, metamaterials have a lot of different properties. What is it do you think about these materials that allow them to catalyze this reaction better than normal materials, metamaterials?
Wow, good question. I think the metamaterial has to do with the shape. Great question. And I think what we're doing is we're shaping a material that already has cold fusion active properties, palladium and nickel.
Mitchell, I would point out that the people that actually work on metamaterials would not recognize your material as a metamaterial. So in a sense, what you're doing is you're saying, people have used metamaterials to shape microscopic properties, dielectric constant, and so forth. And in that spirit, you're using that notion to shape the cathode to influence your experiment. I think it's at some point it's possible to be some confusion in that if you say that you're using metamaterial, folks would expect to see a characteristic microscopic structure that are metamaterials, and yours is, at least in this case, it's just a spiral. So I recommend saying, I don't know, inspired by the notion of metamaterials or something.
We can revisit that.
Can I rephrase his point that can you say with certainty that it's definitely the shape, not the thickness, say, of the film? For instance, if you just create a very thin film over a certain area, would that be sufficient to create, same level of excess energy? So you can say, sure, no.
No, I really believe the shape is key. That's why I use the word metamaterial.
Well, to follow up on the point, imagine a different kind of fuser that was in the shape of a V, so that you localized all of everything that's going on. You could even get more bending if you had a sharper V shape. You could bias it, because.
Good idea.
And that would be one way to clarify things.
Write that down. More work for me. You do the other, I'll do that. Or somebody here ought to join in and help. Let's go back to looking at excess. Any more questions? We'll go back to excess energy measured. Let's talk about what we can see and control. We talked about heat after death, which is what Fleischmann and Pons call the extra energy that came out after we stopped putting in energy from the applied electric field intensity. We call it tardif thermal power because it comes at the end, and the time integral of tardif thermal power is heat after death. We can see it here with this experiment where we're looking at a palladium fuser in heavy water. Here's our ohmic control by power, input and output, ohmic control by energy, input and output. Here's the fuser, input power, output power. And we notice once the electric field intensity is turned off, that we still get, as opposed to the ohmic control, we still get energy coming off the fusor. Unlike some people, I don't see it come off continuously, but that's because I don't use flow calorimetry. With isoparabolic calorimetry, by the way, I know it was mentioned that it keeps going. We don't see it. What we see is it's evanescent with 1, 2, or 3 time constants. But we are able to measure it, and we can actually do things with it. Here, for example, with this run, here's our noise measurement. We're looking at the power from, this is from 1 to 10 watts. Here's our input to the device. Our output is here. This is the energy. And by the way, this is a perfect match. This is, I don't know if you can see it, there's a green line input to the ohmic control, and the output is the blue, and here they overmatch for energy. And here's a really nice system where we get the ohmic control, as Lou Smullen would have loved and liked, right in between these two. But it's real hard to do, but I want to show you, yeah.
In terms of your heat after death, there's been a lot of discussion as to how it works. in other experiments, around the time that Fleischman and Flons presented years and years ago, and they saw it at SRI, they saw it in other laboratories, so we're thinking, what's going on for this heat after death? Namely, we have to maintain some loading, you imagine, to get the excess heat. And we'd like to have some flux. On the experiments at SRI and the experiments at Fleischman and Flons, the notion was that you had a reasonably large cathode, so you had a large reservoir of deuterium. You get your loading at the surface, but when you turn the current off, you're not loading any further. What's happening is the deuterium is coming out. So you get your deuterium flux. Meanwhile, your loading's going down slowly, so the excess power is going down because you're losing your loading. So that's the basic picture. And I think that's probably consistent with your experiments here. The question then would be, has anybody ever seen any heat after death in a co-deposition experiment of copper, for example, where there's no reservoir? Or in a LANR where there's presumably locally no reservoir.
Or how about covering the cathode at that moment of incipient heat after death with mercury or something,
Then you
where it
block
can't
the
leak
flux.
out?
You block the flux.
Yeah, more experiments to do. Write that down, please. Again, this is open turf. For me, cold fusion has been like the Louisiana Purchase. I mean, it's just one thing where nobody's ever looked, and we keep walking. And even in this lecture, we end up getting 3 more ideas for experiments. So here we see, for example, here's our noise measurement, and here this is the noise measurement in the ohmic control system. And here we see the heat after death coming down to the same level. But again, you're right, we don't know the mechanism, and that would be a good way perhaps to look at it better. When we do discharge spectroscopy, we see multiple regions, but it might have to be a geometric nature, it might be different sites deloading. We had a lot to learn about. One thing we did is, this was our first run back where we took the energy from heat after death and used it to do work at another location. So it really is real. Here was our first use of tardive thermal power, or heat after death, to heat up a second bucket of water. And so here, for example, we see, here's our ohmic control system. We ended up heating that up with the heat after death. And here we can see that now again, this is log, okay? So here we're up at a watt, and here it's coming down and cooling and heating up the second system. But it was the first time where we actually took what we were perceiving as heat after death and proving, in fact, that we were getting energy out of it by heating up a second volume. I don't know how much time we got left. Are we already running over? Do I trust that clock?
About 42 minutes or so.
Oh, good. Okay, well, one thing we have here is we see that the tardive thermal power has different regions, which, as Peter points out, we don't really understand what it is. It may have to do with discharge and perhaps from different regions. So again, I've never seen where heat after death continues. For me, either in the case of nickel, there's minimal heat after death. We get a lot of heat after death with loaded palladium systems, but I've never seen it continue indefinitely. It always goes down. We did a lumped parameter analysis to try and determine how big these populations were. This is what we calculated if you want to work it out. Again, the papers are over there. We found that we could control heat after death, which gave us another 4 times control of output. And basically what we found, there's 2 ways to control heat after death. You can do it by, for example, driving your system so you have more regions of,
Eventually, you should go back to your last geograph and explain what this are, because that's a really important geograph.
This one?
Yeah.
Okay. I got to jump ahead of here to do it. What we discovered was there were 2 issues here. I got to think of how to do this. When you drive a cold fusion system, you apply a certain voltage in order to begin the drive. We found, for example, when we took this system and drove it at 300 volts, we got this much excess power out. This is just heat after death. And the time course goes like this. So we turn off the electric field. We're getting out 1.3 watts of heat after death for free. We're measuring an open circuit voltage. Now, by open circuit voltage, I mean we take our cell, we've already charged it up, there's no other battery or Thevenin equivalent or Norton equivalent driving it, and we put it into a Keithley electrometer so we don't discharge it too quickly, and we measure our open circuit voltage, that's VOC. And what we find here, for example, at 300 volts, is we're getting out 1.3 volts excess energy for free. I mean, we put in before, but we're getting it out for free now. And over time it falls down to 0.7, and then the heat after death disappears. Okay? 0.7 was crucial. Now what we found out was that when we drove the system, we got more excess energy out in heat after death, the higher the voltage. It goes up sort of like the square. And you can see it here. When we drove it at 115 volts, we got this much, which deteriorated down here. 200 volts, deteriorated down here. 300 volts, deteriorated down here. And that is where this comes from. When we take, thank you, by the way, for having me do that. When we take now the integral of that extra energy that we get out after we've done the experiment and looking at what we call excess energy. Now we're looking only at heat after death. This is the gain in the experiment. But if we include heat after death when we drive at 500 volts, we get this. If we drove it at 350, we get this, at 200 that. Okay? That's why a lot of people may not have seen it when they only drive it at 20 volts or 10 volts.
So there's like two things that independently are really interesting about this. One is that in this experiment, the amount of energy that you're getting in the place where you're not got any current flowing is actually more than the excess energy produced when you've got current running. And the second thing that's interesting about this is you're showing this nonlinear rise with your
Yes.
with your applied voltage.
And a third one, which is that when the VOC goes to 0.7, it shuts off. But it allows you to do design experiments where you drive it and you stop it, and you're not putting the energy in.
If you go back to that again, one more question, sorry.
Which one?
Back another, perhaps.
Yeah.
In this case where we are loading at, say, with driving at 200, 350, and 500 volts.
Yes.
Is this a case where by the time you're up to 500 volts, you thinking of the operating optimal point, you're going beyond the operating optimal point?
No, we drive it at the OOP.
Okay.
And then we shut it here. I'll show you right here. This is one of these runs. We're picking a drive level where we've already characterized the device.
Okay,
So we're picking the OOP, we're driving it there. It's a good point. I got to think about what you said. It's another way to look at it. I think it may not be. I think they're not all at the OOP. There's two separate effects there.
because the heat after death was going up as the power, the voltage.
The voltage,
was going
applied
up.
voltage, yes.
The energy you had in the drive phase was not. I was wondering, maybe even going down a little bit. I was wondering
Yes.
if that was perhaps suggested that we're.
I think you're
working
correct.
beyond
Yeah.
Is that the same system with three different?
This is the same system. This is the same system. I think you're right. I think we're driving slightly beyond, but we get the benefit of the heat. It's a good point. I got to rethink it.
So these must be for runs where your time when you had the current on was like shorter.
Yes.
You're minimizing
Yes.
the time in order to maximize.
Yes, exactly so.
Can you comment how the current changes when you change the voltage from 200, 350, and 500 volts, approximately? You change the voltage and the current obviously does change.
I don't have that with me, but it's a good question.
This really is an interesting point. It almost, as Peter suggested, if maybe it's a case where you're loading it in the drive phase and when you turn it off, it sort of deloads. It's almost like inhaling and exhaling.
Well, that's exactly the picture for the breathing mechanism in the SRI experiments. I'm not even as very closely related. in addition, in the energetics experiments with the superwave drive, you're sort of varying the current rapidly in order to push things in and out.
It looks like you're maximizing your flux, which
Right.
might be suggesting that's one of the key points for getting your energy is to
Well,
have
it's several issues. Here, the question is what is it that's going on microscopically for heat after death? You turn the current on, and things continue by the database we have for the other experiments. You've got to have loading. Because the reason heat after death is going down is because you're losing loading. You've got to have flux, and flux is going down because the deuterium is breathing out and fluxing out when the current goes on. And that's good enough to drive the system.
and sort of to get the maximum energy out of the whole thing, you probably want to sort of tune your breathing, get the right amount of inhale and exhale.
That's right.
Well, for these fuser experiments, that seems to be a good idea.
Does the amount of time that you see heat after death correlate to the amount of time you drive it? If you drive it for 1,000 minutes, you get heat after death. For 100 minutes, if you drive it for 200 minutes, would you get any different amount of heat after death interval?
Don't know. That's a good question.
In other experiments, the heat after death seems to be sort of fixed. You know, you get a few hours of heat after death. If you run for 100 hours XSE and you turn it off, it's a few hours of heat after death.
That's what I think.
Which is
Almost
sort
if
of
there's a
consistent
limited
with the time-
capacity that you can
the
fill
time
it
of
and
decay.
try and fill more of it.
Let's look at some motor systems. Again, what we did here is use a redundant system where at the core we had either a cold fusion device or an OMA control. We do isoparabolic calorimetry locally. We measure the heat flow coming out. We then put it into a Stirling engine. The Stirling engine we do calorimetry on as well, and then we measure the rotation rate. And so, for example, this is what it looks like. They're actually, the devices are in here being driven. And I think I can show you.
September 14th, 2006, run 35. The cold fusion driven engine on the right is moving, while even though more energy is supplied to the OMA control on the left, there is no engine motion.
And it didn't matter that one was
September
stuck. I mean, we
14th,
would switch the two back and
2006, run
forth.
35. The cold fusion driven engine on the right is moving.
All right, so let's go back to, yes. Okay. What we did, we started in 2004 with using Stirling engines. And in our initial 11 experiments, we got an average gain at the base of 150 to 170% excess energy. And motion only on the side. Well, that's because I drove it at a level where we wouldn't get enough heat in the OMA control. I mean, if we got rotation here, this would really be pumping along. But it made a nicer demonstration when one was turning and one wasn't. So we did two sets of phases of experiments. These are our results. And the other thing is, when we drove the Stirling engines, we found that there was an optimal operating point for these two. Again, what we did is it's a redundant system, so we were measuring the delta T at the core, the heat flow out. We had some miscalibrated heat flow sensors. We were measuring the delta T at the engine. We actually also were generating electricity at the same time, and then looking at the motion for the engine. And so we had 4, 5, and 6 ways of confirmation. I'll show you some of them. So for example, at this run, we're looking at delta T at the Stirling engine. And here we're running from 1 to about 1,800 minutes. And here's our OMA control. This is delta T at the engine. So this is way down the line compared to the core. And we're still getting more out from the fusor compared to the OMA control. Here is our calorimetry at the core. Here's our input power to the ohmic control, our output from the ohmic control. These two are over here. Again, it's a nice match when it's right in between. Here is our input to the fusor. Here's our output. So this difference is our excess power gain, and here's our excess energy. And because we shut it off here, here's the heat after death. We're getting used to, hopefully you're getting the pattern recognition to see all this now. So we get a nice match for ohmic control, and here's our heat after death. Here it ends. Here's our excess energy, and yet it keeps going up for a little bit up to here. This is, we weren't using pure palladium. We were using titanium as well. I won't get into that now. Here's our, this is our input power to the ohmic control. Less is going into the fusor. Here is what's coming out here. Jumping ahead, we're looking at, this is the degree C over the power in. A lot of times what we do is we look for the rise in temperature and divide by the input power. We call that normalized delta T. And that allows us to compare different systems, one to another. So here, for example, we're getting, for our power input normalized delta T from 1 to 3,000 minutes. Here's our palladium fusor versus the ohmic control. So when you do input power normalized delta T, you can get your energy gain by the ratio of these two. Yes?
In principle, your ohmic control should give you like a constant, always the same. And the fact that your ohmic control lines are curving a little bit is a signature that you need to run these things a little bit longer to get past
That's
the
right.
relaxation point.
That's right. So you don't want to take the ratio of this to this. We do it here to here. Or here it's not quite reached it. That's exactly right. And of course, these are three different levels of input power. We're again looking for optimal operating points and driving them at different systems. Peter's right. So here, for example, this is the heat flow. This is input power normalized heat flow. This is different, a totally different sensor from the last one we looked at. Here, these are miscalibrated heat flow devices. So we take a non-heat conducting tube, we put this in the middle, and we can measure the heat going through it. And we find for the fusor, when we divide by input power, we get this, and the ohmic control is here. And this ratio, again, shows excess energy. So again, for example, when we go to the nanomaterials tomorrow and we show what we did at the demo, we'll show you three different ways that we measure the excess energy. The delta T, input power normalized, the heat flow, input power normalized, and in the case of these, we'll show you the electricity generation and the motors, and with the nanomaterial, we'll also show you the calorimetry. Here, for example, is the calorimetry, where we're looking, again, input power on this side and output power. Energy's over here, so these curves are read off on the right. These curves are the power, they're read off on the left. This is between 0 and about 2,000 minutes. Here's our input to the ohmic control. Here's the output. You notice we can almost capture all of the heat. This is because we're having the heat go to the Stirling engine. We're not going to capture it all. In the other systems, we could, because it was relatively insulated. Here, we're letting the heat escape to go to the motor, and that's why we're not quite coming up to it. And here, we're not coming up to it at all. But when we bring it up, we see, again, this is nice because the ohmic control is right in between our input to the fusor and the output. And here's our heat after death. This is looking at delta T of the engine, not even of the core, but of the engine itself. 6 ways of confirmation. This is where we add electricity and the motor and so forth. Here, by the way, the input to the fusor device is the exact same as the input to the ohmic control. So these three curves are overlapping. And here's our excess energy here, a little bit of heat after death. Okay. This is the heat flow, input power normalized. Again, as a function of time, you take the ratio of the two when you do this to get the energy gain. Now this is interesting. This shows that what we're measuring is not an artifact. It turns out that when we extracted all of the heat to the motor, we lost the over-unity at the core. And here you can see it. So for example, here, there's a lot of curves here. Again, I apologize. Let's see how I can explain this. The input to the cold fusion device is here. Here's our output. So we're over unity. And over here we turn the engine. With a Stirling engine, you have to start it. So this didn't have enough energy to start, so we started it here. Once we began extracting energy, we lose the excess energy at the core. We're only getting excess energy outside. I don't know if we're going to have time for this. In dual adjacent this was an idea Peter had. When we were initially doing dual ohmic controls, we had two completely identical calorimeters. And Peter suggested, why not put them together? And that was interesting. We call that dual adjacent calorimetry, and it let us do an artificial house, and we could model having two rooms. And that was interesting, but there's a lot of crosstalk. But it did have excess energy recorded. So in our initial dual adjacent calorimetry experiments, see here you're looking at the fuser heating up the fuser volume, but because the calorimeters are next to each other, we also have the fuser heating up the ohmic control over here, and vice versa. Makes the analysis tougher, but we were still getting energy gain. And here, by delta T, it was 150 times, 150% compared to input. Sometimes in some of the papers, you'll hear about type B anodes. And what we did is, instead of using, we used a big on-phos plate for the anode. And that also made, it made for nice movies. And here you see the fusor. This is a thermocouple right down dead center. And here's the plate. And there's a whole bunch of other physics that comes out of it. I'm going to quit, not do that. This is the impact of deuteron addition to the nickel light water system. I shouldn't say light water. No, I don't think anybody's ever done an experiment with light water, but ordinary water, which is essentially 5,999 parts and 6,000 is ordinary hydrogen. And that was here. So we're getting a modest excess energy gain. And we start adding heavy water and we get this. And we found the more heavy water we added, the more excess energy came out, meaning it might be in nickel that the D is the fuel as well. We don't know. Here we see the impact of adding the up to 15% heavy water boost to the ordinary water system. And as I told you, if we drive it too hard or put too much in, we damage it. And here you can see an actual picture of this. Let's take a look. This is what the our fusor looked like. This is wound nickel that we would put in. And if we overdrove it, we would get a damaged fusor. It would change color. The electrical resistance would change from 8.8 micron centimeters down to 8. But the important point is the damaged fusor was exactly like a control. We never got excess energy out again. Yes?
Mitchell, the thought was that heavy water experienced DV, there was evidence for helium 4 coming up. And so in the light water case, the thought was maybe it's H and D going to helium 3. Now, since nobody's done a helium 3 measurement, the only way you can also get any information about it is maybe if you add a voltage of deuterium to the little bit that's already there, maybe the system will notice it, respond, and get more helium 3 made. So the fact that you saw more excess heat with small additions of deuterium is consistent with an HD going to helium 3 mechanism.
It's a good point. And obviously the ionizing measurement experiments we do now, we probably ought to add that to it when we get done with the NANR. So please write that down. That's more work for me. The trouble is, every one of these ideas is probably 3 months of work or more. And we're already up to a year and a half. What's the matter? It's only 11.
No, it's It's 2 hours off.
Somewhere it's 11.
Bermudas.
Do you want me to keep going, or should we stop? We can skip
Passed
this.
the, last time.
Pardon? Hold on. Oh, it's 1 o'clock. We are over. How far did we get? Well, there's 2 more sections in light water. We could take a break till tomorrow if you want. And one section will be on non-thermal emissions, and the other one will be on direct electricity production. Okay? So why don't we call it time if it's been 2 hours, and we'll come back tomorrow. Any questions?
Too many questions on heat after death.
You had great suggestions.
I have a question on the, when you're doing the Stirling engines, you mentioned that down in the system, it was no longer over unity when you were using it. I didn't quite understand what was happening there.
I don't either.
Did the system itself stop producing over unity, or was just the heat being extracted out?
I think we were extracting the heat. I think what's happened is it's not